Cherapanamjeri, and I'll be presenting on our STOC 2023 paper, What Makes a Good Fisherman? Linear Regression under Self-Selection Bias. This is joint work with my collaborators at Berkeley and MIT, Yeshwanth, who will be a postdoc at MIT next year, Kostas, and Manolis, who will be a professor at Yale. Okay, so if our question was actually what makes a good fisherman, a reasonable approach towards an answer would be the following two-step procedure. First, we might go out, say, into a village, and collect a bunch of data. For example, for each individual in the village, we might collect a vector of their features, for example, their height, their weight, their speed, as well as how good they are at fishing, which we might measure using, say, their income. After collecting this data, we'd fit some kind of model, say a linear regression, predicting the income from the features, and we'd hope that this model gives us a good idea of the answer to our question, what makes a good fisherman? Now, the problem with this approach, and the problem that motivates our entire study, is something that's known in economics and a variety of fields as the self-selection problem. We don't have data from people who didn't choose to fish and instead chose to do anything else, what we might call unrealized fishermen. So to make this more concrete, let's say this is our village. In this village, there are a bunch of people. Each person has a set of features. And let's say in this village, there are two possible occupations, hunting and fishing. So the villagers, being rational people, each try both occupations and see how much they would make. So for example, they might try hunting and observe what their income is if they hunted. Then they might try fishing and observe their income there. After doing this, they'll pick whichever occupation gives them the higher income, in this case, hunting. The second villager will do the same thing, and so will the third, and so on and so forth. Now let's say we go out into this village and we collect data. What we'll observe, if you look at the graph on the right, are the solid circles and squares. And if we try to run our regression predicting what makes a good hunter and what makes a good fisher, we'll end up with the following lines of best fit. Whereas what we actually wanted to measure are these solid lines of best fit. The problem is that we don't observe the hunters on the right who chose to fish instead, and the fishermen on the left who chose to hunt instead. And so our goal in this paper is to ask, given this self-selection model, can we still estimate the true parameters, W hunt and W fish, that generated people's underlying skills at each occupation? I want to start by illustrating a few examples of self-selection, showing that this isn't just a problem that occurs when measuring people's occupations. So the first example is the example we just went through. We had individuals, each with feature X. Their fishing income was given by some noised linear model of their features, and their hunting income was given by a different noised linear model of their features. The twist, however, was that villagers were strategic. They chose the profession that would give them the largest income. And because of this, our observations look like features, the income from the higher paying profession, as well as the profession they chose. And our goal, recall, is to estimate the underlying weight vectors for hunting and fishing. For another example, take SAT score reporting. So let's say we have a student with features X who's applying to some university, and this university mandates SAT subject tests. The student might take the math subject test and score some score, and take the science subject test. The student, however, isn't going to report both of these scores because the university only wants them to report one score. Instead, the student is going to report the score that is more likely to get them into university. And so the student might look at some historical data and figure out what their probability of acceptance is given their math score and what their probability of acceptance is given their science score, and only report the highest score as well as the subject test. So we might get observations that look like a student's features, their score on the science test, and the fact that they chose to report the science test. And our goal, again, is to estimate what exactly is important for scoring well on either of these tests, given just the strategically reported data. For one final example, we can look all the way back to 1972, where Fair and Jaffe proposed this market disequilibrium model. And in this model, we have a whole bunch of houses with some fixed set of features x, as well as a candidate pool of buyers who are all looking for houses with feature x. Now, at any given point in time, there's some amount of supply in the market, which we might suppose is given by a linear model of the house's features. And there's some demand, which again, we might write as a linear model of the house's features. We don't actually observe the amount of supply and demand in the market, though. All we observe is the number of houses sold, which corresponds to the minimum of the amount of supply and the amount of demand. This setting is slightly different than the previous two because we don't even observe which of the two we're seeing. We don't get to see if the market is demand constrained or supply constrained. We only see the house's features and the number of transactions made, which corresponds again to the minimum of the amount of supply and the amount of demand. And our goal, as always, is to estimate what features are important for supply and what features are important for demand. Or in other words, the underlying linear parameters. Even though I've given 3 examples here, there are actually a wide variety of examples of self-selection bias in everything from economics to the social sciences to education. And most existing theoretical results in this setting focus on either identifiability results or asymptotic convergence rates for simple models of self-selection. In this talk, we'll focus specifically on self-selection in the context of linear regression. I'm first going to overview the setting and the exact problem statement we're looking at, and then we'll look at 2 settings of self-selection, which we call the known index setting and the unknown index setting. And then I'll wrap up with some future directions. Okay, so let's begin with the setting. In this problem, we have a set of k ground truth weights. These are just vectors in RD that correspond to the parameters of k linear models. There's also a known selection function, which takes these k outputs of the linear models and outputs which linear model we're going to observe. So S, for example, might be the argmax function. The data generating process is as follows. We sample some covariates x from RD. These are just features. We then compute k different potential outcomes that are given by the dot product of these features with each of the parameter vectors, each of the ground truth weights, plus some mean zero independent noise, which we'll actually assume is Gaussian. Given these k potential outcomes, we're only going to observe one, and the one that we're going to observe is given by the selection function. So for example, we might observe the maximum, or we might observe some other function, but it's a known function of the k model outputs. We then either add x I star, the index we're observing, and y I star to the training set, or, for example, if we think back to the market disequilibrium example, we add only x and y I star, and we don't observe which index we're looking at. We call these 2 settings the known index setting and the unknown index setting, respectively. In both of these settings, our overall goal is to get good estimates of W1 through WK, these ground truth weight vectors. Okay, before diving into our techniques and results, I want to highlight how this problem is slightly different from previous problems that have been considered. Here I just have restated the data generating process, and I want to highlight a couple of things about this problem setting. First, the problem is non-trivial even when we know the true index I star. So this corresponds to the known index setting on the left. And if you recall from the Hunter and Fisherman example, things aren't exactly trivial when we see I star. Second of all, the choice of which I star we see is endogenous to the model. Third, what we're after are finite sample and ideally efficient rates for these problems. Fourth, we're hoping to look at fairly general selection rules S and not just the argmax. And finally, the estimates of the parameters themselves, these WIs, affect I star in the sense of if I have an incorrect estimate of a parameter WI, I'm also going to incorrectly estimate which model output I'm looking at. And so there are a couple of related problems. One is mixtures of linear regressions. And in mixtures of linear regressions, This S function is not a function, but actually corresponds to a uniformly random choice of the K models. And this differs because if we knew I star in this case, we would just be running K separate linear regressions. There's another setting called censored linear regression, where instead of observing, where we only have one model, and we observe its output if the potential outcome yi is above a given threshold. But again, this doesn't have the endogeneity. Estimates of whether or not we're going to see a given yi are totally independent of the parameters that we're estimating. A very related problem is so-called max-affine regression, studied in this recent paper by Ghosh et al. This problem, again, becomes trivial once we know when I star is shown. And for those not familiar with max-affine regression, it's actually a very similar setup to ours, but rather than having independent noise values for each outcome, there's a single noise value, and the selector is applied before the noise is applied. Finally, probit regression resembles our setting, but without even observing yi star. And while there are algorithms for solving probit regression, these don't usually have finite sample efficient rates and work exclusively for the argmax selector. Okay, so now that we've gone over the setting, I'm going to highlight our results and algorithms from both the known index setting and the unknown index setting before wrapping up. Okay, so in the known index setting, our results look something like this. Under some mild assumptions that I'll overview in the next couple of slides, using n observations from the known index model, we can construct estimates that approach the true parameters at a rate of log n over n. O here is hiding some polynomial dependencies and some problem parameters that we pretend are constant, and the running time is also polynomial n and all of the problem parameters. Okay, so we first need a couple of standard regression assumptions for this to work, and these are that the features have bounded norm, that the weights have bounded norms, the ground truth weights, and that we have some amount of covariate thickness. That is, there isn't a single direction where there's no variance. The second assumption we'll need is something called a survival probability assumption. So the insight here is that, the intuition here, is that if, for example, we had no hunters in our village, if every single person chose fishing, then we would have absolutely no way of estimating what makes a good fisherman, because there are no fishermen in the village. And so what we need is for there to be some constant alpha, such that every potential outcome is observed with probability at least alpha over k, where k is the number of potential outcomes. So in our hunter and fisher example, we need there to be some constant alpha, so that each person has at least alpha over 2 probability of being a fisher or being a hunter. And we're hoping for a sample and time complexity with respect to alpha to be poly 1 over alpha. Our final assumption is on the structure of the selection function S. So in our hunter, fisher, village example, what we observed was the maximum of all of the potential outcomes. But we'd also hope to handle slightly more complex selection functions. For example, in our SAT score example, the student first looked up their probability of acceptance, then reported the score that would maximize their probability of acceptance. And the criterion that we come up with in our paper is something called the convex inducing slice assumption. And what this means is that for every potential outcome, if we fix a value of that potential outcome, then the set of the rest of the outcomes, such that outcome I wins, is convex. And so to give a visual example of what this means, here's an example of a set that does satisfy this assumption, because for each value of y1, the set of y2s, such that y1 is the observed outcome, is always convex. It's always a line segment, a continuous line segment. On the other hand, this selection function S would not work, because for most values of y1, the set of values of y2 that would make y1 be observed are 2 disjoint line segments, which are not a convex set. And just to give a little more intuition here, things that automatically satisfy this assumption include both the argmax operator and also any selection function of this form, where we have some set of monotonic functions, we apply each monotonic function to its corresponding potential outcome, and then select the maximum of the monotonic functions. Now that we've established these assumptions, we can state our result a little more precisely. So under the discussed assumptions, now with n observations, we can construct estimates w1 through wk hat that approximate the true parameters at, again, a rate of log n over n, but with a polynomial dependence on the number of models, the survival probability, the noise variance, and the assumed bounds on both the feature and weight norms. And the running time, again, is polynomial in the number of observations, the dimension of the feature vectors, the number of potential outcomes, the survival probability, the noise variance, and the assumed bounds on feature and weight vectors. Okay, I want to spend 1 or 2 slides highlighting our approach here and then move on to the unknown index setting. So our approach here, in short, is going to be gradient descent. And so we're going to first write down the population log likelihood function. And so here we're going to write capital W star to be our true unknown model, and W to be our current estimate of the model parameters. And so this population log likelihood first averages over observations, then pretends to have an average over infinitely many samples from the true model W star, conditioning on the specific set of features xj. Now, in reality, we only have one sample from this, but the population log likelihood averages over infinitely many samples, y star and I star, sampled from the true model. And then inside this expectation, we just have the log probability of y star, yi star, and I star evaluated under the current estimates of the parameters w. So this is a pretty standard log likelihood calculation. It turns out, and we show in our paper, that this population log likelihood is strongly concave, and that its unique maximizer is at the true unknown model parameters w star, and most importantly, that we can estimate its gradient efficiently from samples of our known index self-selection model. There is a bit of nuance in this third step where it requires sampling from a truncated distribution that has a pretty low survival rate, and we give a Langevin dynamics-based solution to sampling from this. But again, the details are deferred to the paper just for the sake of time. And with these 3 criteria satisfied, we can just apply projected gradient descent on the log likelihood. And I'll omit the features here, and again, redirect any interested people to the paper. Okay, so that concludes the known index setting, and I want to spend some time talking about the unknown index setting. And in the unknown index setting, again, collecting n samples involves first sampling some covariates xj, same as the known index setting. Again, computing these potential outcomes, where we have k potential outcomes for each xj. Selecting an I star based on the selection criterion S. So far, everything is exactly the same as the known index setting. Now, the key is that we only add xj and yj, which corresponds to yi star, to the training set. We do not, the learner does not see I star. And so the challenge here is that we no longer have a concave log likelihood that we can just run gradient descent on, and in fact, even identifiability is not obvious. And as we'll see later, in the next slide, in fact, identifiability isn't even true for some selection criterion, for some selection functions S. And our results in this setting are, our main results are identification results for the maximum selector with general K. So for any number of models, we can identify the weights, assuming that the selector S is the max selector. And under the special case where K equals 2, which pops up in a lot of places, like the market disequilibrium example, we have an algorithm that has polynomial time and sample complexity in all relevant parameters. Okay. In order to tackle the unknown index setting, we need 2 additional assumptions. First, we need to assume that the covariates themselves are standard Gaussian random variables. So in the known index setting, we had no assumptions about the covariates. They could be any set of covariates X, so long as they satisfied the covariate thickness assumption. Here, we need them specifically to be standard Gaussian. And second, rather than the convex inducing convex slice inducing criterion from the known index setting, here we require that the selection function S is just the argmax function. And so what we observe is actually just the max of the K models. Okay, so I'll give a quick sketch of one of our main results, which is the identification result, showing that given samples from this unknown index model, we can identify, if we had infinite samples, the K weight vectors W1 through WK. And our approach is going to be through induction. So the base case is rather simple, because if we had K equals 1 model, we're just looking at a standard linear regression problem, because there's only one model to take the max over. We're just observing X and Y from a linear regression. And so what we're going to do is then run induction on K. So now suppose K is greater than 1, and assume that the CDF, the cumulative distribution function of X and Y, identifies the parameters when selecting out of K-1 models. And then we want to argue that if the CDF identifies K-1 models, it must also identify K models. And so the main idea here is that we're going to look at the tail, or the high moments, of the distribution of Y given X. And this distribution is going to be driven by the largest norm weight. And because of this property, maximizing what's called the pth directional moment actually identifies this largest weight. We'll then try to peel off this largest weight and try to simulate samples from a maximum of K-1 weights, after which we can just imply our inductive assumption. And I'll try to make these 3 steps much more clear on the next slide. Okay, so to make this more precise, again, let's assume we have K greater than 1 models, and we're observing features X and the maximum of these K models, and further assume by induction that the CDF, phi of X comma Y, identifies any K-1 of these models. So if we just had samples from X and a maximum of K-1 models, we would be able to identify the weight vectors. So the first step is to define what's called the directional pth moment. And so for any unit vector, the directional pth moment just looks like a standard moment calculation, with the exception that in the expectation, we're conditioning on the fact that the projection of X onto the null space of the vector V is 0. And we can do this because we are just trying to prove identifiability. So we can assume that we have infinite samples, and we're excluding any X whose projection onto the null space is non-zero. We then prove that the limit of this directional pth moment as p goes to infinity for even p is directly related to the maximum projection of V onto a given weight vector. Or it's driven by the maximum inner product between V and a given weight vector. And so by searching over V's and looking for the V that maximizes this limiting moment, we find, up to sign and scale, we find the direction of the largest norm weight vector. And so once we've identified this largest norm weight vector, some extra work, which I won't talk about here, helps us identify the sign and the scale of this weight vector, and so we can fully identify Wj star. Once we've done this, we'll start collecting samples not from xy, but from this new distribution xy tilde, where we define y tilde as y minus Wj star times x. And so the idea here is we're going to try to peel off the effect of Wj star on this unknown index model. So if we write down the distribution of y tilde, it's now going to be the maximum of a standard Gaussian, because that's the model that corresponded to yj star, and the other k-1 models. And so if we write down the CDF now, the CDF of y tilde is going to look like the standard normal CDF, because again, that's just an independent standard Gaussian variable, times the CDF that's given by a maximum of k-1 linear models. And so by constructing this new distribution, which is given by the CDF of x and y divided by the Gaussian CDF evaluated at y, we can simulate the CDF of a k-1 weight unknown index model. And once we've done that, we can just apply our inductive assumption and we're done. We've identified the weight vectors. I'll briefly talk about how we turn this identification argument into a highly inefficient estimation algorithm. We first find an O of k dimensional subspace that contains the weight with high probability. And we do this using an application of Stein's lemma. We then directly adapt the identification argument into a finite simple algorithm. Once we've adapted it to a finite simple algorithm, we'll just apply this algorithm to the O of k dimensional subspace that we've identified in the first step, and the result is an algorithm whose runtime is exponential in both the number of weight vectors, and actually O of the number of weight vectors, and in poly 1 over epsilon to get epsilon accuracy. So obviously this is not ideal, but the benefit is that we only pay in the number of weight vector and not in the full dimension of the space. And for k equals 2, you'll find the details of this in the paper, but we also have a fully polynomial time algorithm. In terms of takeaways and future directions, again, just to reiterate, our contributions in this paper were estimation results for linear regression with self-selection bias under both the known and unknown index settings. In concurrent work, also done with the same set of collaborators, we also have results for non-parametric density estimation under self-selection bias with applications to estimating auction models. And that paper appeared at EC 2022. In terms of future directions, first of all, one that's not written here is improving the rates of estimation for the unknown index setting, which are currently quite expensive, but then also going beyond linear regression and potentially to less structured noise models. So our current results heavily depend on the fact that the independent noise applied to each model is Gaussian. And finally, extending to unknown selection rules beyond just argmax or convex inducing ones. Can we actually extend to the case where we don't know S and we have to simultaneously learn S with the parameters we're interested in? That concludes this presentation. Please see the paper on arXiv for more. Thank you.